Hello. Well, okay. Welcome back to another one of my video recording sessions where I talk about genetic algorithms. Or is it just one genetic algorithm? Or maybe different ways of doing the same genetic algorithm again and again and again and again. Forever. I don't know. But maybe that's the point. The point of doing genetic algorithms is to never end, maybe. But I think I'll save this rant for another time. So, well, welcome back again. The date time is 2025, July 1st, and the time is 9:24 p.m. Yes, it is still the same day as the date time when I did my very last video, the previous video. And today, as I said in that video, I will go through I'll try to go through all the three different ways of doing pseudo-chaotic genetic algorithm. I named it Prototype 1, Prototype 0.1, but they're like three versions of the same version. I don't know if that makes sense. I'm not totally decided yet. I just cannot make up my mind yet. But well, maybe I have made up my mind, but I don't know. But regardless, I'll go through all the results. I'll try to go through all the significant results in this video, in this session. Yeah. So, in the first type of the prototype, this way of doing chaotic genetic algorithm, or pseudo-chaotic, to quickly go over how this works, is that three groups in red, in gold, I think this is, and in purple are selected, and each group is to go through one entity event. So there are three entity events, so one group, one event, in this very specific order: mutate, learn, and procreate, MLP, not related to multi-layer perceptron. I think that's the right abbreviation, right? Yeah, multi-layer perceptron. But anyway, I didn't mean that to be the same, in the same, spelled the same, or in the same order. Anyway, so mutate, learn, and procreate, and all the other entities, or all the other stars that have not been, circled or enclosed or chosen or grouped, will just be idle during that time step, during that blip. Now here, blip is a time step, is a unit of a time step. So all the stars, all the entities not in any one of these groups will just be idle for that time, for that blip, and these three groups will go through one entity event each, and when that is done, when the last group, this purple one, for example, has finished its procreation part, and the procreate function being used would be random selection procreate. So the two parents are randomly selected, and then once that is done, towards the end of the time step, towards the end of the blip, the selector function will find which entities have actually gone over the maximum constraint threshold, and strike those out. And the pop limit function will limit the population if the population of entity is above the maximum population, and that will be the end of one time step or one blip, and then the whole cycle will continue from continue on until it's over, until the for loop reaches the maximum number of blips, or maximum number of time steps. So this is the first way of doing this. Other things are mostly the same. I may have made some slight changes, but no major changes were made. For example, the learn candidate percentage is now meaningless, since that is somewhat incorporated when choosing this group for the learn group. So if it's set to 20, we'll just be choosing 20% of all entities randomly. Yeah. So the candidate percentage, learn candidate percentage, and the candidate method is both have been rendered obsolete. However, the learn rate is still intact, so the entities will still be assessed and ranked, and given their own individual mutation rates and learn rates. Apart from that, and the rest is the same. And well, what else? Anything else to do? Nope. So the first results were used. Let me go here. Yep, it's no. My mouse is kind of broken. So the first iteration, the first run. Now there are these three terms: mutate ratio, learn ratio, and procreate ratio. Now what these three mean, what I mean by these three words is that there. So these three words mean the ratio of let me just, this time, not a brush, let me use this. No, that's too small. No, I'll just keep using this. That is so bad. Okay, I'll just use this. Sorry about the delay. So, what I mean by these three words is that the mutate ratio is the ratio of entities given all entities, maybe 1000 entities. If this mutate ratio is set to 0.45, It means that the group chosen for mutation will contain 450 entities. If the learn ratio is set to 0. Let's do another number, 5.2. These are just arbitrary numbers. Then the group for learn will be comprised of 520 entities, because there are 1,000 entities. If the procreate ratio is set to 0.11, the group for procreate will be 110. Now, these two are kind of it's easy to understand what these two will do, but when it comes to the group for procreation, the group of entities that will be used in for the procreate function will not actually all be parents. It's just that the group of entities that are chosen in this group will be considered as candidates to be parents. So not all 110 entities will give birth. It's just that a few, that the chosen 110 entities are up to be considered to be parents. The rest, no, not in this blip, not in this time step, not during this blip or time step. And again, regardless of how these entities are enclosed by one of these circles, the ones that are not, the ones that are not in any of these groups will be idle. They'll just do nothing. I just cannot stress that enough, seems. So, having said that, the first iteration, named chaos 2025 0625 _0, the mutate ratio and the learn ratio and the procreate ratio in this particular order is 0.3, 0.3, 0.3, and the number of items is 100, so it's 100 genes. And the population size in this case, for these 4 runs, I made, I didn't know I was making this mistake, but for these 4 runs, I made the population size grow from 100 to 1000 without thinking about it, for no reason at all. Because this was usually done when I had the number of items starting at a smaller number and grow in tandem. In this case, this should not have been like this, but I did it anyway. But I felt that there's no harm in sharing this. And this is how the distributions look like. So you can see, well, what is it? Here, 11. Yeah, doesn't matter. Yep, there we go. You can see that the mode is 2860, and the top is 2860, and with the mode being 2860, there are 696 entities at the mode, and the top is the mode. So there are about 70% of entities at the top, which is the mode, but it is not the true ceiling, because the true ceiling like I've always said, is even for today's video is still 2865. So, and you might wonder if, you know, what if there was a true ceiling? There had been a true ceiling, but you know, it disappeared. It got struck out. Well, that, if that were the case, I would have had the maximum ever at 2860. But recently, I found out that the code I was using to record these metrics and well, generate these plots had a few I wouldn't call it bugs, but you know, I had a few mistakes that I made that somehow and sometimes left out some of the true ceilings, if ever they happened. So not all of them, but sometimes some of the true ceilings were missing even when they did happen. So I kind of fixed that. At the same time, I came up with a better, well, I thought what I'm about to show is a better way of assessing how the settings for an evolution iteration performed, or how good or bad or how robust it is or how diverse it is. So what I would do is I would go through all the chromosomes of all the entities that have existed during that iteration and find the number of unique true ceilings, true ceiling 2865, and on the right is that result. So if you look right here, this is 0625 underscore 0 and 0625 underscore 0, and the number of unique true ceilings, or the unique true ceiling count, is 0. So that's why I have these two. Well, they're they're two parts of the same document, but that's why I have this weird setting, so that I can show side by side. So that's what happened. And the next run I did the same, and I got just about the same results. I'll just quickly bring that up. Distributions, not this, not this, this. Yep. So here the top is 2860 and the mode is 2850. Again, 657 entities at the mode, which is 2850. So very close, very close to the true ceiling, but not so quite the true ceiling. So anyway, that's what happened. However, no true ceilings were found. So that's when the mutate ratio, learn ratio, and the procreate ratio, the three ratios, I should call them, the three ratios, or I shouldn't actually say it like that, it just sounds ridiculous. The three ratios are at 0.3, 0.3, 0.3, still nothing, no unique true ceilings. And when I lowered the learn ratio to, this is not to be confused with the learn rate. I know I said I would change it, but not there yet. So this is not the same as learn rate, but anyway, for the third run I changed the give me is it better? Yeah, that's a lot better. So for the third one I changed the learn rate to 0.2 and guess what I got? This is 25.2. 25.2. Again, 0 unique true ceilings. Well, let's have a look at that. So that's 2. What was that? Oh yeah. So 0 unique true ceilings, no unique true ceilings rather, and something weird happened right here, but not that weird actually. It's the first era anyway. So I thought I saw something, but it's not. I was wrong. And for the next one, it was 0.4, 0.2, 0.3, and that's again no true ceilings, no unique true ceilings. And even when let's skip this one, _4, _5, the mutate ratio. See the logic here. My train of thought here was that maybe I wasn't adding enough of a, maybe I wasn't providing the entities providing the entities with enough opportunities for them to change during the entire run. Maybe that was the case. Maybe, and so in order to well, fix that, I tried to, and then yeah, in order to fix that, I raised the mutate ratio, but maybe in case that was too much, I also lowered the learn ratio, or what used to be called the learn candidate rate percentage, from 0.3 to 0.2. Oops. Yeah, that's what I did. But then, still, no true ceilings. So on to the next one is where this is strictly speaking, if I change the number of items from, for example, from a smaller number to eventually and gradually to a bigger number, and along with the population size, then this is per the definitions that I have been laying out for the past several months. This isn't just chaotic genetic algorithm. This is already chaotic dynamic dynamic genetic algorithm. It's not just chaotic genetic algorithm. It's kinetic. It's not kinetic. It's chaotic dynamic genetic algorithm. But I just didn't mention that here. I kind of mentioned that right down here when I started changing the the constraint values and the utility values. But let's just stick to this here. When I did, I saw that I wasn't doing it right, or not entirely right, so I changed the code so that the number of items would start from 10, along with the population size starting from 100 and increase to 100 and increase to 1000. And the three ratios were 0.3, all of them. And what happened? Well, nothing. No true ceilings. So, in the next run, I raised the three ratios. Oh, hold on. I should show you this. I should show this as well. So here we go. Here's the first era, second era, third era, fourth era. Now here the distributions look kind of different from the ones that I had for the past few months. and that's because well, this is where I realized that I need to change where I measure the metrics, so I did that. But it's usually about the same. They were, and you'll see that when I show the other when I show the other entity distributions, we'll be able to see that. In the next run, I raise the three ratios, all of them, so that they all equal 0.5, or 50% of all entities would be chosen. Of course, some entities could be in more than one group. So when I did that, I got 10 unique true ceilings. And here's the distribution. Again, this is that time when I didn't fix it yet. I hadn't fixed it yet. I mean, that's almost like really pretty, but you know, that's not the case. Well, we can just have a look at the sum utility plot. This is what it looks like. So they behave in a in exactly the same way as, well, that we're actually quite familiar with by now. So 0.5 works as in yields true ceilings. In this case, we got 10 from it. Now, three ratios, because it went from 0.3 to 0.5, what about in between 0.4? What would happen? Let's find out. And I got I got 2 unique true ceilings. Okay, that's good. Yeah. So let's have a look at that. Distributions, yeah, I still hadn't fixed it. Yep, we still see the staircases. And in the next one, which is _9, we're back to 0.3. You know, just in case, I just wanted to see if I could get the true ceilings. Turns out, nope, no true ceilings. 10, 0.35, 0.35, 0.35 were the three ratios. Again, namely mutate ratio, learn ratio, and procreate ratio. And what happened? No true ceilings. Okay, maybe, and then this is where I thought maybe I need the three ratios to be somewhere around 0.4, or at least 0.4. So I did that again in this run, _11, and I got 7 unique true ceilings. Okay. We see the staircases again. That's good. Now back to 0.5, which is for 12 _12. What happened? No true ceilings. Still, this indicates. So this still indicates that it is still very, or quite, based on luck. Even with the same setting, you might end up with 10 unique true ceilings. Now these are unique true ceilings, and with the same setting at 12, we might get none, like here. So and this also proves further proves it. Underscore 13, 0 unique true ceilings when we had the three ratios equal to 0.4. Again, 14, 0.4 again, 0. 15, 0.4 again, 0. 16, 0.5, 0.5, 0.25. Now this is when I felt that maybe I could also try a setting where the three ratios aren't exactly the same. So 16, 0. And let me just show you. Let's see that. Now I fixed it. The problem was that I was measuring right as a new era had started. So I would get that nice, very sharp bell curve. But towards the end of one era, it's normal that you get this. So this is with, what is it? 0.5, 0.5, 0.25 for mutate, learn, and procreate. We see that the distribution shapes are largely the same, but even for 16, no true ceilings right here. We have for 17, underscore 17, we had 7 true ceilings. Now let's have a look at the settings. It was 0.4, 0.4, and 0.25. So seems that 0.4 still does the job, and the procreate ratio can be a bit lower. So yeah, that's what I got from that. Procreate ratio can be lower than 0.3, but not the same for the mutate ratio and the learn ratio, because they're largely, well, they are the main driving factor. And for underscore 19, 0.4, 0.4, and 0.15. Again, got unlucky. 0 unique true ceilings. We raise the first two ratios, mutate ratio and the learn ratio, to 0.5, 0.5, and the last one, the procreate ratio, to 0.1, and for that we got 0. Is that right? So for 19, it was 4, 4, 15, 0.4, 0.4, and 0.15. We got 7 of them. Okay, that was kind of lucky. Yeah, so I just read that wrong. I was wrong. So, and underscore 20, no true ceilings. Underscore 21, I changed it and I lowered the learn ratio from 0.5 to 0.4, whereas the mutate ratio stayed the same, and I increased the procreate ratio to 0.2, and that gave us 0 unique ceilings. 0 unique true ceilings. 22, 0. What was 22? 22 is, now this is different. This is something different that I that I implemented, a new change. Before, if an entity was the top entity, its individual mutation rate would be 0, which is of course smaller than, which is of course lower than the base mutation rate. And the I should draw. Okay, here's the world. What was that? Go on. No. Here we go. So, this is the world. This is the head entity. This is the tail entity, and this is the rank. So, and this is the individual mutation rate, if you are the head entity, your mutation rate, or let's just do it here. This is the median entity, and give me purple. This would be the mutation rate right in the middle, the base mutation rate. And if you were the head entity, it would be at 0. If you were the tail entity, very likely to be double the base mutation rate. That's how it was. Okay? Now, what this means, as in lowest equals base mutation rate, I wanted to, I thought that all these entities being at the mode and the mode being the top, at least like 45% to 70% of all the entities all being stacked up around the top value, around the top summed utility score, and making that the mode is kind of a problem if that's above 45%. You know, I would like that to be lower, because that's like about half the entire population at around the mode. So to do that, and this happens because, well, whether you are selected like in any one of these groups or not, if you are very, very high at the top, as in somewhere here, you get a very low mutation rate, like 0.001-ish or 0.0, as in terms of percentage. You get a very low individual mutation rate, which means that if you're, it's bad enough, or I don't know if it's already bad enough, but the entities sitting idle won't change, because that's the definition of being idle, and the entities with high summed utility scores, or with the highest of the utility scores, even if they were chosen in a group of mutation, because they would have very low individual mutation rates, they wouldn't change. And that is why this phenomenon happens. So many entities at around the very, very end. So that's a problem. I think that's a problem. It's bad for diversity. So what I did is I added the base mutation rate again, so that even the top head entity would have some amount of, now this is the 0, and this is the base mutation rate, and this would, and these 2 points would be, you know, somewhere in the middle. So this would be like a base mutation rate plus something, and this would be twice the base mutation rate plus something, or maybe 3 times, because it's already twice plus BMR, or base mutation rate. Yeah, so that's what this means. So from _22, this is the new norm, and for 22 still had, with the settings, with the 3 ratios being 0.4, 0.4, 0.15, still had 0 unique true ceilings. Ouch. Okay, fine. You know, that's fine, right? I don't know. For the next one, _23, 0.4, 0.4, 0.25. What was it here? 7 mutation and 7 unique true ceilings. So that's this. There we go. Yep. And now with the new setting where the lowest mutation rate is the base mutation rate, which is 0.01 or 1%, now you see that we did get some true ceilings, and the mode is still very, very close, or actually the second highest, next to the true ceiling. But now there are only 52 entities at the mode mark. So now we see that we slightly see the right half of the distribution, or the normal bell-ish curve. Yep. So that did solve the issue. So that's 23 for you. And 24, what did we do? 24, this is when I just tried everything. Now 1.0, 1.0, 1.0. And I think this again proves that luck has a lot to do with this, because even when I was doing it for all entities, and therefore it takes about the same amount of time, which I believe was, let me check, what was this, 24, yeah, 44 seconds. Oh, by the way, all these, because we do end up working with fewer entities in general and in total, they all took about half the time, so somewhere between as low as 10 seconds and all the way up to 30 seconds. So and some mostly 19, 18, 19 and or 20 seconds. So this is time-wise, it has been more efficient. So 24 for all entities all the time, and this only got us one unique true ceiling. Not the best. Here 25, 0.7, 0.5, 0.1, still no true ceilings. Now something happened here. 26, 0.5, 0.1, 0.4. Okay, and we got 12 true ceilings. What's different? What do we do? Not much. It's just that the three ratios were as follows: 0.5, 0.1, 0.4. So it seems that the mutation rate is still so it seems that the mutation rate may be more important than even the learn ratio. No, let me rephrase that. Let me say that again. The mutate ratio might be more important than the learn ratio, and learn ratio might be more important than the procreate ratio. Again for 27, 0.4, 0.4, 0.4, and we got 18. So again, 0.4 has proven to be good default value or a standard value. But now that we are using this setting where the lowest individual mutation rate is the base mutation rate, we got more unique true ceilings. And in 28, this is when I had the void chromosomes off and the random chromosomes on, and even when I did that, even when I added some randomness, even some more randomness to this, I got what was it? 28, 11 unique true ceilings. So that's good, right? Yeah. And 29 is, well, back to 29. This is when the mutation rate was, the mutate ratio is 0.5, and the learn ratio is 0.1, and the procreate ratio is 0.5, and I got 17 unique true ceilings. Okay, interesting, right? without the void or random stuff. Yep. So 29. So I had something different here for 30. I got 13 true unique true ceilings, but what happened here is that I downsized the entire population, so which of course then would take even less time. 30. Yeah, so only about 10 seconds. And the three ratios were all 0.4, and I still ended up with 13 unique true ceilings, which further strengthens my guess that 0.4 is a good place to start with. I mean, the lower these ratios are, the better, because it would mean that fewer entities would be involved in the entirety of the iteration, of the run, of the evolution, and from from blip 0 to maximum blip. That one iteration. The lower these numbers are, the fewer the entities, the fewer the number of entities that are actually involved. So or rather, therefore, less time to compute. It's less compute intensive. So that works. 0.4 is a good number. Usually the notion was that a smaller population would usually lead to a lower degree of convergence, or fewer true ceilings. In this case, maybe, but it still did get there in half the time, or less than half the time, because it usually takes 18, 19 or 21 seconds. This only took about 10 seconds, so half the time. In 31, 46, but now here's something different. What I did here is that I would increase the population size from 100 to 1000, along with the number of items from 10 to 100, but I would change the maximum constraint once it has reached the once it had reached the 10th era. I would go on to change the maximum constraint to a higher one, and then have those alternate. So it would be like 18,000 for one era, for the 10th era, 23,200 for the 11th era, back to 18,000 for the 12th era, 13th, 14th, and 15th, something like that. And by doing so, what happens is, well, interesting. And I have to show this. No, wait, let me show the one with the smaller population first, which is 30. So the degree of convergence, or the ratio of entities sitting at the top, which is the mode, is still 1/3, around slightly less than 1/3, but we still see this very similar distribution. But when we have this setting, where we got 46 unique true ceilings, so that's 31 underscore 31. This is what I meant. this is the 10th this is the 10th era. 11th era, this is where the maximum constraint went over 18,000, so this is 23,200. This is the max value of the higher maximum constraint list that I used to use, and then suddenly back to 18,000 again. So you see, so here you see that all these entities disappeared because they likely got struck out by the selector function. And and they had to well, most of them had to be re-procreated and repopulate the world, and you see them sharply, climbing up within the next 100 blips, and then back up to 23,200, and then back down, and then back up. So this is 1,500 blips, and when this happens, what tends to, under this setting, what tends to happen is that there would have been some true ceilings right here, and then because so many entities got to transcend that setting, that true ceiling, and then got erased, and then transcend again, got erased, and got transcend again, it potentially led to a more diverse an environment. It potentially made an environment that houses, or that is able to, or rather that provided us with a more diverse set of true ceilings. True ceiling for 2865, not 3065. 3065 is the true ceiling for the higher maximum constraint list, but that's not what I was looking for in this experiment. So that's why I think that's why I got 46 true ceilings. But then again, in the next run, I did the same, and I only got 19. So again, luck plays a big deal, a huge part. And then in this next setting, although the three ratios have all been 0.4 for the past few settings, in this one it ends with a lower maximum constraint. So interesting, right? What was it? 33, and I got 0 unique true ceilings. Very unlucky, right? Let's just have a look at that. We have the, yep, you can see that the distribution just kind of teleports from here very close to the total sum of utility values, and then in the next era they shift to the left, because now it's what this means that the max constraint is now lower. So all the entities that were above here had to get struck out. That's not what I was here for. There we go. So what I mean is that now the entire run ends with a lower maximum constraint. Okay, and when that happens, for 33, in this case I had 0 unique true ceilings, true ceiling 2865, However, in the next run, same setting, I tried again and I got 26. So it's still very reliant on luck. Look at that. See, this is the 10th era, at the end of era 10 or era 9, because it's zero index based. Compare this to okay, and higher max constraint, lower max constraint, higher max constraint, lower max constraint. So if you have a look at this right here, we already have 325 entities at the true ceiling, which is 2865, which is the mode. And then once that era with a higher max constraint comes, like this, and goes, we went from 325 entities at the top, which is the mode, to the mode being 2850, and the top is still 2860, and now we have more of the right half of the distribution, well, the shape, in terms of shape. And then after this, the era after this, a higher max constraint gives us this, where 274 entities were at the true ceiling, which is the mode, which just happens to be the mode as well. 272 in the first era with the higher maximum constraint, and then 274 again, and then when that era changes to an era with a lower maximum constraint, this happens. So when this happens, the shape of the distribution just tends to get a bit wider, but this may be because when they fall all the way down here, the entities are only given 100 blips for them to recover and converge, after which the era with a higher max constraint comes, and then it's easier for them to continue converging to a true ceiling for a higher max constraint. And then another era comes, and then lower max constraints, so a lot of entities die, they go extinct or get struck out, whatever, and then they're only given 100 blips for them to recover back again. So that's why the entity distribution gets wider and wider as this happens. Think of it like a flushing, as this flushing happens. Flushing. Oops, that's not how you spell flushing. Flushing. The entity distribution gets flushed, or rather gets widened. So same thing here for, what is it, 35. I got 30 unique true ceilings. I did a lot of these because it was interesting and I wanted to get it right. And for underscore 36, same setting again, where the max constraint ends on a higher max constraint. Again, 38 for 38 true ceilings, unique true ceilings. Nice. Okay, cool. Now, that was, I did, well, it seems that I have done a lot about, well, about number 1, right? Yeah, it seems so. But now I can have, to be honest, I've done too much. I've done this too many times. I've done it, what, how many times? 36 to, yeah, I've done it 37 times, 37 runs. So, in this underscore 37, I've only done it twice, but it's for this one, the second way of doing it. So, what I did here is, again, select 3 groups, but shuffle the entity events and let them play out. So there are in total 6 different combinations or orders in which the entity events could roll out. Yeah, and the point or the purpose of this was to see if I could still get unique true ceilings, or if I could get true ceilings by doing this, and how many or how diverse they would be. And in this case, the 3 ratios were still 0.4 because that just somehow proved to be quite a defaulty or standard-ish value for the 3 ratios. I could be wrong, but anyway, underscore 37, and I got 19 true ceilings, 19 unique true ceilings, right? Yeah. And let's have a look at the distributions. What's interesting is that it's the number of entities sitting at the mode, which also is the top, isn't that high as I expected it to be, but this could be, this could be different depending on, for example, which one of the 3 entity events happened in which order the most, or which, yeah, I think that's so. But anyway, because it could be different every now and then. Let's have a look at the some utility plots. Yep, 37. Yeah, so about the same. Nothing, weird. So, and we did get 19. And the next run, in underscore 38, I kept on alternating the maximum constraint value for 100 items, between 18,000 and 23,200 again. And I got 12 unique true ceilings. So let's have a look at that. So one, yep, higher max constraint, suddenly lower, back higher, suddenly lower, and that's it. Right? Yeah, I'm right. And by doing this I got 12 unique true ceilings. Okay, let's have a look at the entity distributions. Here we already see that it's giving us a wider, more of a robust entity distribution shape, and then higher maximum constraint, lower. See how it got widened or flushed? Widened. Let's just say widened. Yeah, and then back up to higher. Now going from here to here it's easier because no entities had to get struck out and disappear or vanish, but suddenly after disappearing, because of a lower maximum constraint, Now it's harder for the entities to come back up, as seen here. Yeah, so that's what happens. But I still got 12. Okay, 12 unique things, unique true ceilings. Okay, let me take a sip of water. Okay, I'm back. So, in the next runs that I'm about to show you will be the third way of doing a pseudo-chaotic genetic algorithm. And this is where three groups are selected. Entities are... Yeah, three groups are selected, each containing some ratio of the population in the world at that blip, at that time step. And in this case, the three ratios being, for example, all 0.4, 0.4, 0.4 doesn't really matter. It's just that I use the same variables, but nothing guarantees that the group that were made using the variable called mutate ratio with the value of 0.4 is going to end up going through mutation. It all depends on what the entity events, what the set of entity events will be after running, in terms of Python code, random.choices, and then we insert mutate, learn, and procreate, and set k to 3, which will in total, which may in total give us 27 different combinations, because it's 3 times 3 times 3, and that's per blip, per time step. So now we have no way of knowing, for example, if you just wanted to look at this entity right here in a given blip, we have no way of knowing what this entity will go through at the start of that blip. So it's more chaos now, more randomness, and that is this one, 39, with the maximum constraint eventually capping at 18,000, and we had one true ceiling, 2865. And this is what the summed utility plot looks like, and this is from the previous run, where it was from the second way of doing pseudo-chaotic genetic algorithm. You'll see that this blue squiggly line, which is for the for the tail entity, the bottom entity, it's still quite jagged, it's still quite rough. You know, it shoots up, it comes down, it shoots up, it comes down, something like that. But that tends to be even more so in this case. And this is because the entity events are the set of entity events are way more different. Now there are 27 possibilities. And if you have a look at the surface of these stairs, they're more jagged, they're rougher here, because we have no way of guaranteeing that, for example, mutation will happen. It may happen, you know, it's not a low chance, but it could still not happen. Or if, for example, procreation, you might have procreation in one blip or not. So that's why this all the lines look more jagged, random, more squigglier rather. So one unique true ceiling, onto the next run, which same setting, but in this case I got 28. So luck still plays a huge part. Next one, same thing, 41, 19 true ceilings. Let's have a look at the entity distributions from 39. This is what the entity distributions look like. Yep. We see that we have more of the right half of the distribution. This is when we had one true ceiling, one unique true ceiling. And compare this to this. This is when we had what, 12 was it? No, 28. 28 true ceilings. But we still do have this bit of, well, this partial right half of the distribution. And the mode in this case was, you know, was the true ceiling, as you can see here. And the next one, 41. Yeah, about the same. Cool. Oh. Sorry, I forgot to mention. For the second time, I tried the three ratios to be 0.4, where I got 28 true ceilings. That was good. The one after that, when I got 19 unique true ceilings, the three ratios were lowered to 0.3, which should not have worked, or hadn't worked up until so far. Like here, all these times when these three ratios were at 0.3, they never actually managed to produce any true ceilings. However, doing it the third way, using random dot choices, I did get true ceilings. How many? Well, quite a lot, 19 of them. So yes, luck does play a part, a huge one at that. But it seems that using random choices, or using random choices to decide what the set of entity events will be during a blip, during a time step, may be better. And all this still takes half the time that it used to, when compared to doing everything in a sequential manner. And in the next run, underscore 42, it's 0.2. The three ratios are 0.2, 42, and I still got 6 unique true ceilings, which again is quite surprising, because it wasn't supposed to work. It had never worked with such low value for these 3 ratios. So that's good. So random choices might be good. This third way of doing it seems to work better. And let's have a look at the distribution. Yeah, so it did work. Nice. And we do get that some bit of the right half of the distribution again. I guess that's good. And the next one is 43. This is when the 3 ratios were at 0.1. So 43, and I got 0 unique true ceilings. Okay. And this is what it looked like at the end of the iteration, at the end of the run. This is the entity distribution. This is what I got, but still no true ceilings. And here we go. We see that now everything is a lot less smooth. So yeah, that's because fewer and fewer entities are involved, which means that more entities stay idle, which means no change. So you see these these tail entities just staying where they are, unless they're somehow involved in one of the 3 in any one of the entity events, which are also random. And so I raised the 3 ratios to 0.15, all of them, and that's 44, and I got 6 unique true ceilings. Yep. So okay, let's have a look at the distribution shapes. This is the final one. Yeah, it looks nice. We still have the top, we still have the mode, somewhat close to the true ceiling, that is 2865, and the mode is 2850. Yeah, it is still missing that right tail, but this is well, kind of robust, so I think I'm fine with that. And in the next run, again, I wanted to try alternating the max constraint for 100 items, just to see if it would give me more unique true ceilings. 45, and I only got 2 of them. Yep, up, down, up. So only 2. Did I get 2? 45. Yeah, only 2 unique true ceilings. Entity distributions. Wow, that looks nice. Yeah, okay. Cool. See, this is when the lower maximum constraint is in effect, and you'll see that the top is only 2620, which means which could be a lot closer, which should be a lot closer to 2865, but only given 100 blips, with the three ratios being at 0.15, they're not given a lot of opportunities. The entities are not given a lot of opportunities, enough opportunities for them to converge to the true ceiling, which is why the top entity, the head entity, is so low in terms of sum utility value, and the mode is also so low. So that's sad. Again, 12. But since the converging continues on when the higher maximum constraint kicks in, and then the entities are able to converge, and then we do have the true ceiling 3065 for the higher maximum constraint list. Same thing happens here again. Yeah, still not enough convergence here, and then enough convergence here. So that's why I think we get only 2, well, and a bit of unluck as well. Misfortune here as well. We only get 2 unique true ceilings. 46, we got 11 of them. But what happened? Well, still this the same setting, except that the whole thing ends on the lower maximum constraint, 18,000. And here are the distributions. There we go. This one, in this run, I think things got lucky, because the entities are more converged when compared to what is this? This one. So compare this to this. These two have the same maximum constraint in effect. However, this one is more converged. In this run, underscore 46. In underscore 45, that wasn't the case. So, still, luck plays a huge part. That's all I can say for now. My job would be to make sure to maximize the use of luck, if that makes sense. I don't want to be always relying on luck, but create some kind of a system or a environment that is very friendly, very welcoming, very inviting to that element of luck. So that was 46, and I got 11 unique true ceilings. And here I think I can just quickly go through this one. This is more dynamic. Like I said, even these were chaotic and dynamic, but this is more dynamic because now in these runs I changed the constraint values. I had the constraint values being dynamic, and where is it? And the utility values being dynamic in these last 4 runs. So, where is it? Yeah, it's this one. So in this one, in this first one, chaotic dynamic 25_0, I had 5 unique true ceilings. So what I did here is I had the three ratios at 0.4, and I was using the first way of doing this, so fixed entity event order. Yeah, and when I did this, the lowest individual mutation rate was 0 for this one, and I ended up with 5 unique true ceilings. So that's what this looks like. Same thing for this one as well, but now in this case I got 8 unique true ceilings. Okay, in the next one I got 0. I wonder why. Because I used 0.3 for the 3 ratios, which again, under normal circumstances, or under this first way of doing things, is terrible at creating or providing true ceilings. Okay. Next one is _3. This is where I changed it to random choices, which is the third way of doing this. So 27 different sets of entity events, and the lowest individual mutation rate is the base mutation rate, is equal to the base mutation rate, and the 3 ratios equal 0.15. Okay. And the maximum constraint just ends at 18,000, just in one go. 3, and I got 1 true ceiling. See how the plot for the tail entities look like a like a skyline of a city. Here are the distributions. Okay, we do have the right half, some of it. We do have the true ceiling, so that's good. Okay, moving on. In the next one, what did I do? Again, dynamic constraint values, and 3 ratios at 0.15. Right. So same setting. 2 unique true ceilings. Okay. Alright, okay. In the next one, what did I do? The 3 ratios have been raised to 0.2, but I still only, or rather, unfortunately, I ended up with 0 unique true ceilings, because of luck, I guess. Yeah, this is just purely bad luck. I don't, because of bad luck. Is it bad luck? I don't know, but yeah, that's. Alright. And same for the next run. 6, 0.2, dynamic constraint values, yeah, 0, so I don't Yep. And same for underscore 7, 0.2, same. So 0.2 seems to be not such a great value when I have dynamic constraint values. What's this? 0.25. And I got 3 unique true ceilings. Okay. Wow, look at that convergence. Again and again and again. So 0.25 seems to work wonders. Okay, that's good. I mean, the default, the standard was 0.4 for the first way of doing pseudo chaotic, but now it's around 0.2 or 0.25. So that's, I think that's an improvement. For the next run, 2 unique true ceilings. What did I do? 0.25, same setting. Yeah, I don't think I need to see that. We need to see that. Oh no, we do need to see that, because now the utility values are also dynamic. They would change per blip. Wow, look at this pretty shape. Alright. Notice how the values are not what we are familiar with. This is because the metrics were measured during that blip, where the utility values were also, varying or changing by each blip. So they would be calculated on a different scale, or using a different scale. That's why they're different. But when computing how many true ceilings there were, I would use the fixed versions of the 2 sets of values, utility values and constraint values. So that's how I know. In 10, what happened? No luck there. In 11, no luck there. Even when I raised the 3 ratios from 0.3, from 0.25 to 0.3. Okay. And 12, I got 14. What happened there? I just got lucky, because it was the same 3 ratios, but now I have 14 unique true ceilings. Let's have a look at that, because that's the last run of today's video. That's what happened. Okay. Wow. Okay, that's decent. Okay, so I think that's about it. But I think the takeaway for today is that doing things, at least doing things in a pseudo-chaotic way, may, or it definitely has one benefit. It takes less time, because now these entities in this, no, because these entities are idle. Not all entities have to be involved in some kind of a entity event. So less time to compute, less time to simulate. That's one huge thing, because it used to be 38 seconds, and then 20 seconds. Now it used to be 40 something seconds. It used to be 70 seconds. It started from 70 seconds to 40 seconds to 38 something seconds or 30 seconds. Now it's down to 20 seconds, and the shortest it took was 10 seconds, or was it 9? Let me see. Okay, depending on how I do it, it was 8 seconds. For 43. What was 43? This took 8 seconds. Where the base mutation, no, where the 3 ratios were 0.1. And what did that give us? 0. 0 unique true ceilings. But I'm sure that would work like 1 out of 10 times. I'm not that sure, but I can kind of be sure. So that's good. Less time is good, and they behave in almost the same way. Now the only question is, this was pseudo chaotic and also dynamic. Regardless of, now the only thing that I am curious about is, regardless of how I implement it, will things be the same if I succeed in making everything chaotic? My guess is that quite probably yes, but I have to work hard to find that out. So that's about it for today. Wow, that was almost 100 minutes. Well, thanks for sticking around. See you next time. Bye.